overcurrent based on what? Based on the protection needs and the protection function to be used. Okay, and based on the design itself. So we will explain what is the operating principle of the overcurrent, how to use the current as a fault criteria, and how to differentiate and distinguish between the trip time and the time grading for different steps or multiple steps, and the tripping characteristic, the most common tripping characteristic, for example, the DTOC or the IDMT, and then we will test the time overcurrent protection using the test universe software. So firstly, now we will talk about the operating principle of time overcurrent protection. Okay, so the overcurrent protection function is used in the medium voltage switchgear, for example, it's used as a main protection. Okay, but for the high voltage levels, like high voltage and extra high voltage levels, voltage switchgear for underground cables, it will be used as a main protection. Okay, so we have different kind, as we explained. We have non-directional overcurrent and we have directional overcurrent. What is the main difference? The non-directional overcurrent protection can measure only the current flowing in each phase, as shown here in the our screen. So here is the protected object. Can be overhead line, can be bus power, can be motor, can be underground cable, and so on. And this current transformer will transform the primary values into a very small secondary values, so can be handled and can be withstand with the protection relay analog inputs. And based on the criteria and the parameter setting, the relay will take an action and will have to process or make processing for this current values. And after that, based on the current measurement, it will take an action. Okay, so this action, after distinguishing between the normal operating state and the fault state, so the protection relay will issue a trip command if there is any fault to trip the circuit breaker and to isolate the fault current. So the non-directional overcurrent only using the measurement of the current as a criteria. Okay, so there is no any directionality. Only overcurrent with time grading to provide selectivity of the protection relay. But what if this selectivity is not enough? Okay, so now we are using the current and the time grading. But what if the usage of current and time grading is not enough for providing the selectivity and the sensitivity in your protection testing, okay, or in your protection power system protection in your substation? So in this case, we will need one more criteria to define the directional of the fault. Is it in the forward direction or in the reverse direction? So the directional overcurrent relays additionally measure the voltage for each phase. Okay, so by comparing the angle between the measured voltage and the measured current, the directional overcurrent relay can define and can decide if the detected fault in the forward or in the backup direction. Okay, for sure, if it's the forward direction, so it will issue a trip signal to isolate the circuit breaker. Okay, to trip the circuit breaker and to isolate the circuit breaker. Okay, but if it's in the reverse direction, which means the fault is not in my protected object, so I will give the chance to the other protection to trip the fault current. But if it's not, there is a backup protection also can be tripped with a time delay. Okay, so here is the current is the only criteria to detect the fault in case of non-directional overcurrent. But if you have a directional overcurrent, you will need the voltage measurement to determine the direction of the fault. Is it in the forward or in the reverse direction? Okay, so as we explained in the medium voltage, the overcurrent protection mainly used as a main protection with a time grading or multi-steps. Like IDMT or DTOC tripping characteristic, but in the high voltage application or extra high voltage protection application, it will be used as a backup protection to provide a dual redundancy of your protection system. Okay. Now we will talk about the fault criteria. As we explained, now we are talking about the current, and there is a gap, as we explained in the second topic. There is a gap should be provided between the maximum overcurrent or the maximum load current of the protected object, which can be indicated here IOC max, and the minimum short circuit current. Okay, just to distinguish and to differentiate between the normal operating state, as you can see here, and the fault state. Okay, and there is two different parameters here called the pickup and the drop of values. The pickup can be, in other terms, can be defined as the start signal, which means if the current exceeds, if the measured current exceeds this pickup predetermined value, so the protection function will be started, but not tripped, will be started, and it will keep monitor the current. if it elapses, if the protection trip time elapsed, it will issue a trip command to trip the circuit breaker and to isolate the fault. Okay, and here is the drop-off value, which means the end of fault detection. So the backup or the start signal here represented the start of detection of the fault, but the drop-off here is the end of fault detection. Okay. And I pickup for sure it would be higher than and larger than the I drop off. And if you look at the standard or SEC checklist, for example, you will find out there is a reset ratio which should be greater than 95%. And simply the reset ratio is the drop off value of the current over than divided by the pickup value. And this reset ratio should be more than 95% to just make sure that the protection relay is working in the permissible limits. Okay, now we will talk about another example. Not the current itself as a criteria. Now we have a time grading. Okay, so the overcurrent protection is used as the main protection, as we said, in the medium voltage protection. Okay, but the current protection criteria itself is not sufficient for fast and for selectivity of the fault clearance. Okay, so to provide and to ensure the selective tripping, it's common to use the parameter time as additional criteria. So now we have two criteria. The first criteria is the current. The second criteria is the time. Okay, to provide the time grading between two steps and to provide selectivity of your protection scheme. Okay, so as you can see here, the protection scheme shown in our figure. Here is the time. Here is the trip TA for relay A, TB trip time for relay B. And if you have a fault here, so the TB should be having shorter trip times and should isolate the fault. Okay, to provide the selectivity and ensure the stability of your protection schemes. Okay, so as you can see here, there is the time grading, which is the delta T minimum, which is the time difference between the trip time of protection relay A and trip time of protection relay B. So in this way, the relay A will give some time for relay B to trip. Okay, now we are preventing the unselective tripping without any unnecessary conditions. So if the fault occurs in the section of B, there is no meaning to trip the circuit breaker at bus bar A. Okay, because in this case we will lose the loads here and the loads here without any reasons, because the fault is here and the line between A and B is still healthy and there is no any fault condition here. Okay, so to provide the unselective tripping, we will use the time to make a time grading between the relay B and the relay A. So for this, for example, for this fault, the relay B will have a shorter trip times and it will be responsible for tripping the circuit breaker and isolate the fault current. But what if relay B didn't operate in this case? Okay, so we have to implement a backup protection for the relay B, which is the relay A in our case with larger trip times. So the relay A will take an action if the relay B didn't trip, but after a time delay, which called here delta T minimum. So for selectivity reasons, there is a safety factor called the delta T minimum. Okay, this delta T minimum is a safety factor for the trip times between the section with section A and section B, and it must be considered in the protection design. Okay, so delta T minimum D can be represented in the summation of the T response of the protection relay tripping time, which can range from 35 up to 50 milliseconds, for example, can be also the including the circuit breaker time, which opening time of circuit breaker ranges from 40 up to 80 milliseconds. Also can be also the tolerance time, okay, for the protection function, which can be from 10 to 20 milliseconds. So the summation of the circuit breaker time and the tolerance time and the response time of the protection relay, we have to calculate in the design stage to identify the most suitable delta T minimum. We explained how to use the time as additional criteria to the current and how to provide the time grading and what is the meaning of and what is the main purpose of providing a time grading between TB and TA to provide selectivity of your protection testing and to prevent any unselective tripping in your protection scheme. Okay, so here is the protection relay A and B will picked up for sure. if we have a fault here, so the relay B will pick up and the relay A also will pick up. Okay, but what is differentiate between the relay B and the relay A, which is the trip time. Okay, so the fault cleared by the relay B because the relay B have a shorter trip times than trip protection relay A. Okay, so the closer to the in feed, the larger the trip time. So if you are very closer to the in feed, you will have the most large time, tripping time, based on the protection scheme design. Okay, so to provide the selectivity and stability of your protection schemes. Okay, and the far away from the in feed, it will have a shorter trip times. Okay, so here is the meaning of the trip time and the time grading. Now we will take an example about the tripping characteristics. So as we explained, we have most common characteristic for the timed overcurrent protection functions are the DTOC, which is the definite time overcurrent protection function, or the IDMT inverse definite minimum time overcurrent protection function. Okay, and we will see now what is the difference between both of them and what is the meaning of the tripping characteristics. So here is the first example. As you can see here, we have two axes: the horizontal axis representing the current and the vertical one representing the trip time. So once the current is exceeding this current setting, which is I greater, the relay will trip indefinite time, regardless of the amount or the value of this current. So if this value is double the current setting or triple the current setting, it will trip with the same time, which is Ti greater. And this is the meaning of definite time. So if you exceed the current preset value, the trip relay or the protection relay will trip in a definite time, regardless of the value of this protection relay. And that's why in some cases we have two stages of the definite time overcurrent. One stage representing the I greater representing the short circuit protection or the overload protection, and the other one is the short circuit protection, which have very small trip time for sure. So the DTOC is commonly implemented with two stages. The first stage is I greater, the second stage is I double greater. As you can see here, whatever the value of the current, of the fault current, if you exceed the I greater, it will trip with the Ti greater in all cases, and this is the definition of the definite time overcurrent. Okay, but if you have two stages, you will have the I double greater with a greater value of current setting, and the trip time will be for sure less than the stage 1 trip time. So the Ti double greater will be less than the Ti greater to provide fast tripping for short circuit faults. So the first stage in that case will giving you protection against the overload protection, and the second stage giving you protection against the short circuit faults, which is a very high fault current, so it needs a very small tripping times. The second type, which is called the IDMT is the inverse definite minimum time over current protection, and this characteristic can be used also in different stages. So the first stage can be used as standard inverse curve or very inverse curve or long-term inverse curve in the IEC standard or any customized curve. And the second stage will be definite time. So it will be a combination between the inverse and the definite time in the same case, in the same characteristic. And in this case, the inverse characteristic or the inverse step will giving you protection against the overload protection, and the definite step, which is the stage 2, will give you the protection against the very high fault current in case of short circuit conditions. Okay, so here is the main difference between the IDMT and the overcurrent. So the main parameters in the IDMT is the IP, which is the current setting in the protection relay, and the TB. Here the TB is a unitless value. It's a time index, called time index, or time dial, or in some relays called the time multiplier setting. Okay, so it's a unitless, it's not in second. Okay, so Ti greater is in second, can be 0.5 second, can be 1 second based on the parameter setting. But the TB here can be 0.1, 0.2 unitless without any unit, because it's only a time index or time multiplier or time multiplier setting, as you know. So here is how to represent and how to define the characteristic of the inverse curve, okay, by the IP and the TB. But what is the main difference here between both of them? Okay, the main difference here is the inverse curve here is depending on the value of current. So once you exceed the preset value, which is the setting value IP, it will select the tripping time based on the curve selected. So it will define the tripping time based on the curve selected. So the higher the current, the higher the fault current, the shorter the trip times, because it's inverse relationship, right? The inverse relationship means inverse relationship between the current and the time. So the current, the higher the current, the lower the trip times. And here is the basic definition of the inverse definite minimum time protection. So it's inversely dependent on or depends on the short circuit current. As you can see here, if we have fault current here, we will have like trip time. But if the current is higher, we will have a shorter trip times and so on. So here is the main feature, how to differentiate between the DTOC and IDMT tripping characteristics. Okay, so this can be standardized types of the curve according to the IEC or the ANSI code or the IEEE, such as normal inverse, very inverse, extremely inverse, and long-term inverse, and so on. Okay, so here is the main differences between the tripping characteristics. So now I will give you some example of the equation, how to calculate the tripping times based on the selected curve. So here we have the IDMT characteristic in different curves and based on the IEC. So it can be normal inverse, can be very inverse, can be extremely inverse, long time inverse, and short time inverse. And each one and each standard curve here have a different formula. Okay, so if you need to calculate the tripping times, you have to use the suitable formula for the selected curve. Okay, so based on the current, as you can see here, for example, the normal inverse characteristic relationship, as you can see, trip time equal 0.14 over I over IB, all of the power of 0.02 minus 1 multiplied by the TB, which can be double or triple the setting current. IB is the setting current. So if you substitute between the injection current, the setting current, and the trip time or the time multiplier setting used in the parameter setting, you can calculate the expected tripping time using the formula. Okay. Also, it can be checked for any other kind of IEC or ANSI curve. So the TB here is called the time dial or time index or TMS, time multiplier setting, based on the relay vendors. Okay, now we will take an example about the two stage of the DTOC. Okay, so we have here two stages. First stage is I greater with trip time TI greater. Second stage is I double greater current setting with TI double greater trip times. And as you can see, the higher the current, the lower the trip time. So here you can provide both protection against the overload protection using the first stage and against the short circuit faults using the second stage. For example, in numbers, to be clear for everyone, we have the first stage, the current setting equal to 1.8 ampere, and the TI greater is 500 milliseconds. Okay, so here is the lower current threshold and longer trip times. So in the other hand, we have I double greater, which represents the second stage. So we have here the high current setting and the high current threshold with a shorter trip times, which equal to 100 milliseconds. So if the current exceeds 1.8 and it ranges between 1.8 up to 6 ampere, so it will trip with 500 milliseconds, okay, because it will located in the first curve. But if the current exceeds 6 ampere, which is I double greater current setting or current threshold, it will trip with a definite time equal to TI double greater, which is 100 milliseconds. So the higher the current, the shorter the trip times. On the other hand, if you have two stages also overcurrent for the IDMT, so the first stage can be represented in IB current setting and TB, which is time dial or time index, and the second stage will be I double greater indefinite time and TI double greater. Okay, here is a combination between the inverse and the definite time, and that's why it's called the IDMT. Okay, so the first stage will provide protection against overload, and the second stage will provide protection against very high short circuit currents. Okay, so here is the IP can be represented 1.8 ampere, and the TB is 0.1 in unitless because it's not a time, it's just a time index, can be used inside the formula to calculate the tripping time. So the first stage is IDMT, the second stage is a definite time with a high current threshold and short time delays. Okay, for some relays, which is the Siemens relay, the backup value will be 110% from the parameter setting of the protection relay, just to take it into consideration if you are working in a Siemens relay. So the backup value, the expected backup value will be 1.1 multiplied by the current setting. Okay, so how to test the time over current protection using the testing numbers? We have different modules which can be used as a standalone or in a combination inside the same OCC file. So the I greater here, the backup and the drop-off value can be checked using the quick CMC or ramping module or the overcurrent dedicated module for sure. Okay, So the overcurrent indicating module can be used for the overcurrent protection function. But this means also we have a general test modules, which quick CMC or ramping or pulse ramping and static sequencer, which can be used also for testing the pickup and drop off value, for example, for ramping. Pulse ramping can be used also for the pickup and the drop off for the second element or the second stage. Also, the static sequencer can be used for detecting the or measuring the trip time for both stages, state and general testing module called the state sequencer, and also the quick CMC. And the overcurrent modules can be used for all kind of tests using the protection. Using the overcurrent dedicated modules, except the I double greater pulse ramping pickup, which can be done using the pulse ramping module. Okay, so when we will test the overcurrent, we can select different fault types, such as 3-phase fault, 2-phase fault, single-phase fault, and also we can select different fault loops, such as A to N, B to N, B to C, ABC, and so on. So you can simulate different fault loop types and different fault loops, and during each test, we can simulate the current with the CMC test set and measure the response time or trip time of the protection relay, such as the trip time or the pickup value for the pickup and drop off signals. Now I will give you an example for the Siemens protection relay. So here is from the Siemens protection relay 7SA relay manual. So we have two different types of tolerance. The first type is the absolute, and second type is the relative. What is the difference between the absolute and as a relative one? So as you can see here, the absolute is a definite tolerance levels in millisecond or in milliamp and so on. So it doesn't depend on the current setting. But the relative, it's a percentage from the setting value. As you can see here, 3% from the setting value or 1% from the time and so on. So it the tolerance definitions in relative and absolute, if you are using a general test module, such as a quick CMC, ramping, pulse ramping, test sequencer, and so on. Because in the general test module, you have to define the assessment or the tolerance level of the protection testing. Okay. On the other hand, if you are working with a protection testing template or protection testing library, you will find out this values is ready-made for you, and it's inserted inside the test object tray files, and you don't have to worry or you don't have to enter it manually. Okay, just I'm explaining to you, if you are starting from scratch and if you are using the general test modules, you have to differentiate between the relative and the absolute test values. So let us talk in numbers to just make it more clear. So if we have first stage equal 1.8 ampere, so the relative tolerance based on the Siemens relay manual is 3%, right? So if we calculate the 3% multiplied by 1.8 ampere, it will be equal to 54 milliampere. And the absolute tolerance is 10 milliampere. It doesn't depend on the relay parameter setting. It's independent of the relay parameter setting. So whichever is greater, we should take into consideration. Now the relative tolerance is greater, which is 54 milliampere is greater than 10 milliampere for sure. So we will use the relative tolerance in this case. So the current operating range should be ranges from 1.8 plus or minus 54 milliampere, which can be range from 1.746 up to 1.854 ampere. So here is how to define the current operating range of the pickup value of the current for the first element. Okay. So for other example, for the trip time itself. So the first stage is a definite time with a 500 millisecond. Okay. So the relative tolerance is 1% multiplied by 500 millisecond equal to 5 millisecond. And the absolute tolerance is 10 millisecond. Okay, so whichever is greater, the absolute, right? So we will take the absolute tolerance now into consideration to identify the time range. So the time range should be 500 millisecond plus or minus 10 millisecond, which can range between 490 millisecond up to 510 millisecond. Okay, so here is the tolerance limit defines the acceptable range of the test result. Okay, so it can be automatically assessed by the test universe software. But if we are using a standalone or a generic test module such as quick CMC, ramping, pulse ramping, test sequencer, and so on, you have to select the greatest limits or tolerance limits, okay, to allow the test universe to make a correct and precise assessment for the test results. But if you are working with a dedicated test module such as overcurrent module, distance module, advanced distance module, differential modules, so the test universe software will select whichever is greater directly. Just you have to import the relay parameter setting and start your protection testing. Okay, another example for the stage 2, we have I double greater equal to 6 ampere. The relative tolerance is 3% multiplied by 6 ampere, which equal to 180 milliamp. And the absolute tolerance is 10 milliamp. For sure, the relative tolerance is higher. So we will assess the time or the second stage pickup values based on the relative tolerance. So it will be 6 plus or minus 180 milliamp. Okay. So for the time, definite time of the second element is 100 milliseconds. So the relative one is 1% multiplied by 100 milliseconds equal to 1 millisecond. So the absolute tolerance in our case is 10 milliseconds independent of the relay parameter setting. So we will take the absolute tolerance in our consideration. So the time should be 100 milliseconds plus or minus 10 milliseconds. But here is a different features and most important feature to take into consideration, which is the relay operating time. Okay, because normally the relay operating time to take the feedback from the relay binary output to the CMC binary input, it can take like internal processing time inside the protection relay, which can range between 20 to 30 milliseconds. So we have to take into consideration also the internal processing time of the protection relay. Okay, so here is another example of how to do the pickup value, or the pickup and drop off test of the ramping using the ramping module for the overcurrent stage. So as you can see here, we are using the ramping module to define the pickup value and the drop off value of the current stage, I greater. Okay, here we have to define the ramp with some parameters. Okay, how to define the ramp? We need to define the from, which is the start of the ramp, to start 0.8%, 0.8 from the current setting up to 1.2 from the current setting. So we have to define the from and to. Okay, and I greater is the expected pickup value, which is available inside the parameter setting. Also, we have to define the delta I and delta T. Delta I is the step size, and delta T is the trip time, or the step size in time. Okay, so here is, you have to identify the tolerance in plus or minus. Then this tolerance, which is multiplied by the current setting, can be divided by 4 to identify the delta I, which is the step size or the increment size in case of ramping up, or the decrement step size in case of you ramping down. Okay, then you will start to define the delta T, which should be greater than the operating time. Okay, so for example, if you have 100 milliseconds, make sure to make the delta T here 200 milliseconds to give the relay the chance and to give the CMC the chance to detect the binary inputs. Okay. So now we will take how to assess the result. We will take the start contact, which is the pickup contact from the relay binary output to the CMC binary input, and we will define the trigger condition to be trigger condition from 0 to 1, which means the start contact will be normally open in the beginning, and it will transfer to normally closed to be closed after detecting the pickup value. So the start will change from 0 to 1, and here is how to check the pickup value. And once the test universe detects the trigger condition, which is the start contact in one condition, it will immediately start to ramp down the current until it reaches to the drop off value, which can be defined here. The trigger condition start from 1 to 0. Okay, so here's how to define the ramping modules, how to test the I greater. Now we will talk about the I double greater, which is the testing of the pulse ramping. The pulse ramping is the same as ramping module, but we have additional features here, which is the fault time and the reset time. Okay, so we have from and to, which is the start and the end of the pulse ramping. And as you can see, we have here pulses set and reset, set and reset. So here is the main difference between the ramping, which is a smooth ramping up and smooth ramping down the current with defined step size. But in the pulse ramping, we have pulses set and reset. So we have to identify the two times, which is the T fault and the T reset. So the fault time should be, for sure, should be greater than the TI double greater, which we are using to test the pickup value, and should be less than the TI greater. Okay, to identify and to differentiate between the first and the second stages. And also we have to identify here the T reset to allow the relay to go to its reset state or drop off state before continue to the next ramp. Delta I also, we will use the same formula as the ramping module, which is the tolerance multiplied by the current setting, tolerance multiplied by the current setting, I double greater, divided by 4 to identify the most accurate step size. Okay,